Welcome back. In the last few classes, we have been looking at psychophysics, visual perception, and now last class we looked at now Kalman filter for sensor fusion. All these concepts are very important for building virtual reality environments, but they are not sufficient. To build effective virtual reality environments, we need more concepts. One such concept we are going to see today is called the HCI laws, human computer interfaces laws. We are going to look at all these concepts in terms of the desktop PC, in terms of mobile phones and other devices, input devices, and then finally we will see how this can be adapted to virtual reality environments. If you look at the interactions in virtual reality, or in general, any human computer interfaces, there are several types of the interactions possible. For all these types, a pointing task or reaching task is one of the very basic or fundamental task. Okay, slightly more complicated is now selecting. We not only reach but also select, and then we actually grasp, and then we actually manipulate. So in all these tasks, selection or pointing task is very important. Let us say there is a menu bar in the desktop or in your smartphone or anywhere, or an icon there, and you are using a mouse to reach this menu bar item and select a menu bar item. So in all these interactions, pointing is fundamental. You first reach out the menu bar item or icon and then click on it. That is a selection. So from where you are currently positioned, where the cursor is there, then you have to travel a distance, let us say D, capital D, to go to this icon. This icon or the menu bar has a size, say width W. Given this T, D and W, can we look at can we look at how easily we can reach out? Is there a law which can dictate how easily we can reach out this menu bar items? There was a psychologist called Paul Fitts in 1950s. He looked at this reaching task and then he modeled this reaching task in an equation relating D and W. Okay, this equation is which is shown in the slide is known as the Fitts law. If you look at the equation, it is a linear equation with a slope B and intercept A. Now mt is shown as moment time, and D and W is represented in a logarithmic equation. So this is a log of D by W plus 1 is also known as index of difficulty. So the moment of time is directly proportional to the index of difficulty, and as the width of the icon increases, the index of difficulty decreases logarithmically, and as the distance to reach this target increases, the index of difficulty increases. There is a time this information theory was getting famous due to Shannon, right? So this equation can also be considered as analogous to the information. So the human interaction can be considered as how we can actually process the information fast. Even the reaching using the motor systems and everything together. Now, what is the information capacity? So the The slope of the equation, that is id by mt, is known as index of performance, or the inverse of the slope of the equation. It is also known as the bandwidth and throughput. So index of performance is a nice measure of how well the human is actually performing. Each one of us have now unique index of performance. This index of performance can also be used to compare many devices as far as this reaching task is concerned. So this law becomes very powerful, not only studying this basic task of reaching, but also comparing many devices, many input devices particularly. After FITS, there are many researchers looked at this fundamental problem of reaching in a computer task, and then measured IP, index of performance, in terms of the bits per second. That's a capacity. So mouse has about 10.4, which is same as the human hand. It is 10.6. Joysticks is lesser, 5.0. Trackball even lesser, 2.9. Touchpad even lesser, 1.6. Eye tracker, which may be relevant to virtual reality, that has much higher index of performance, maybe due to the in the eye tracker hands are not used, whereas the other devices, input devices, hand is used. The eye tracking doesn't use hands, whereas other devices listed above, it all uses the hands. Maybe that makes a lot of difference. So let us look at the Fitts law again. The law predicts the time to point at an object or reaching an object using a device as a function of the distance from the target of the object and the object size. So from the equation it is very evident, if the object is away and smaller, we will take more time to locate it and point to it. There is a movement time increases if the d is increases or the size of the object w decreases. And the law is useful for not only predicting the MT but also evaluating the systems for which the time to locate an object is important. Say for example in a cell phone or a handheld devices. So once we know MT or index of performance, we can design the objects in such a way that the index of performance can be increased or the movement time can be reduced, or we can come up with some other strategy where to place it and when to place it. So once we know the index of difficulty or movement time or index of performance, we can decide the size and the distance of each of those items and then try to improve the index of performance or movement time. Only when we measure we can improve on it. And then Fitts law enables this first step, measurement of the human performance in an interacting task. So Fitts first demonstrated this law for the tapping task with fingers. Okay, and then later on he extrapolated to using the mouse and other input devices. As we saw, the index of performance for fingers as well as the mouse is very close to each other compared to other devices. So one of the beauty of this Fitts law is that the movement time depends only on the relative precision, but it's a ratio between the d by w. So the movement time is not limited by the motor activity of moving your head or arm, but rather the cognitive activity of keeping on track of the target. In the slide, there are two targets shown. Each one has now different size, and they are distance also different from the current cursor position, but it will take the same ratio. D by W is the same. Therefore, the moment time will also be the same. This is the main message the Fitts law is conveying. The same two targets are shown again over here. In the top row, the two targets are at the same distance, but the sizes are different. Therefore, the moment time will be actually different. The second target will be easier to reach. In the bottom row, again these two targets are shown, same size but at different distance. So the first target will be easier to reach. So we can use these laws to predict performance on varieties of tasks with respect to the reaching task. Let us say there is a now pop-up linear menu where the list of menu items are now one by one listed. Another pop-up pie menu where the targets are now listed in a circle. Now the question is, which one will be faster on average? Of course, a pie menu will be faster because the target sizes are the same, but the distance is much lesser. Therefore, pie menu will be performing better than the pop-up linear menu. We will look at one concept called infinite height using the Fitts law in Macintosh or Windows or Firefox, how it is used to improve the index of performance. So one thing to notice is that the cursor stops at the edge of the screen. Can we use this fact in order to improve the index of performance? For the purpose of the Fitts law calculations, we can consider the cursor stopping at the edge as having a infinitely tall edges. Therefore, the Macintosh menus or Windows menu, whichever has this particular feature, is faster to navigate because we can reach out this edge of the windows very fast, and then if we put any menus there, it is easy to click, faster to click. That is the idea. Similar features are found in many popular OSs or browsers in the recent time. So to summarize, Fitts law has a lot of impact in HCI. It can be used to reduce the index of difficulty. It can be used to compare the IPs, and we can come up with some strategies to improve the IP, like putting the things in the edges and corners. Are there anything that the Fitts law cannot model? Yes. In the recent time, there are certain interactions which cannot be modeled. This is beyond Fitts law, beyond pointing. For example, there are some nested loops we everyday use for navigation. So this doesn't follow the Fitts law model. As an exercise, you can think about what are the other things that doesn't follow the Fitts law model. To overcome the limitation of the Fitts law, the Fitts law can be slightly modified, such as a steering law. Steering law applies the same principles as Fitts law to steer through a tunnel. So steering through the nested loops is considered as a tunnel. So we have to keep the pointers within the boundaries of the menu, otherwise we will miss out not only that target but also at the boundaries. The equation for the steering is slightly modified instead of logarithmic curve, it is a linear curve. So index of difficulty is now linear, not logarithmic. Let us now consider few points as far as the mobile phones are concerned. How this Fitts laws or steering law can be applied to the mobile phones. The mobile phones can be held in different ways. One way is vertical, another way is horizontal, or we can use it as a tablet or in a docked position. When you keep it in the vertical position, when you hold the cell phone in your hands, only the thumb is available for movements. Whereas the earlier case, desktop, the whole hand is available for input. Here in the cell phone, only the thumb is available for movements. So iPhone actually keeps the menus at the bottom of the OS, which is easily reachable by thumb. Top corners is not reachable. Therefore, no, all the icons that are to be avoided or rarely used, it's all kept at the top. Similarly, the Android also places the OS options at the bottom and the on-screen options such as settings and all those things at the top of the screen, which is very difficult to use or rarely used. When you keep the mobile phone in the horizontal position, both sides, left and right side, are easy to reach for the thumb, but the middle area is difficult to reach. So the middle area we can reserve it for keeping the icons that are rarely used or high risk actions. In the docking mode, the whole hand is used for interaction. Unlike only the thumb in the other two horizontal and vertical mode, the whole hand is used. And therefore, the original Fitts law equation to the entire touch surface is actually valid. But the user will be switching between these three different modes very often. So when there is a switching between these modes, there will be some delay. We need to be cognizant of this delay and the switching, and therefore we need to design the interfaces accordingly. Several studies have extended the Fitts law to virtual reality. Recently, this year, we have 2 journal publications using Fitts law in the virtual reality. In the slide, you see 2 papers. First paper talks about how Fitts law can be useful in training robotic surgeons. Again, we are using the Fitts law to measure the index of performance in a microscopic task, which is now very important for robotic surgeons. The second paper talks about a new conflict that we found in virtual reality. In order to establish that it is a conflict, we use the Fitts law. Okay, we use the Fitts law in the virtual reality and augmented reality separately. When the user get to see the real hand and the virtual hand simultaneously, then the index of performance actually reduces. This is how we establish that there is actually a virtual kinesthetic conflict. If you are interested, you can take a look at these papers. You can download it from our website. So similar to the Fitts law, there are several other laws of HCI which is very pertinent to virtual reality also. We are going to talk about 4 other laws in this particular slides. One is called the Miller's law of short-term memory load, which says that at any point of time, a user can only process 7 pieces of information at a time. It is called the magical number, plus or minus 7 plus or minus 2. If you want the user to remember more than 7, then what we need to do is that now chunking the information, grouping the information into meaningful groups so that the users can easily remember. By the way, this magic number 7 plus or minus 2 is not relevant to the number of items in the menu bar or the list. So the user doesn't have to remember all the menu items, right? Therefore, this number or Miller's law is not limiting the number of items in the menu bar. Usually, now this will be the confusion, but just wanted to make sure that that is not relevant. Another law is called Hicks-Hyman law, which is relating the number of choices and the time for a person to make a decision. So usually the users subdivide the total number of collection of choices into different categories, eliminating about half of the choices at each step rather than considering one by one, which requires linear time. So Hyman later found that a linear relationship exists between the reaction time and the information transmitted when the n is represented as log. The next law is called the power law of practice. When you repeat a task many times, how the time to complete the task is actually reducing. It is reducing logarithmically. This is known as the learning curve. It says initial 50% of the task we can complete it very fast, but the final 50% takes a lot more time to complete. Finally, we are talking about the Pareto and Zipf's law. This is also known as 80-20 rule. It is based on observations back in 19th century that majority of the land in 19th century Italy was owned by minority of the population. So it can be applied to several situations. For example, the linguists initially noticed that most frequent words will occur approximately twice as often as the second most frequent word and 3 times as often as the third most frequent words, and so on. These 5 laws are considered very important for designing human computer interactions. The same laws have been extended to virtual reality also. In a virtual reality, not only hand is used as an input organ, even the head can be used, and the eyes can be used, and the legs can be used to interact. So each one needs separate research into find out the index of performance under all these laws, right? So if you want to find more details of this laws and then adapting this to virtual reality, you can look into this book, The Psychology of the Human Computer Interaction, and in 1983 by Stuart Cord and Allen.